Right. How's everybody doing? Nice to see you too. So, right, let's see. Today, in terms of announcements, I believe you have a homework due, and your next homework will go out also today. This one's on optimization, so you work out some, let's see, a specialized algorithm for embedding a set of points based on their distances, which is kind of similar to a problem you had on the practice exam, but this is a more souped up version. In particular, there's a technique that is used out there called stress majorization, which is also the subtitle of this course, which essentially tries to take a matrix of like pairwise distances between a set of points and then embed them in Rn, respecting those distances as much as possible. So you will implement a particular algorithm for doing that using majorization minimization algorithms. So if you've encountered EM in your machine learning universe, this is an algorithm that falls into the same category, but probably isn't one that you've derived before. And then compare it to the built-in one in Python, and hopefully you'll see that it's a little bit better. So that's fun. So in an event, as always, give it an early try. Make sure you can run the starter code. And as about 5 of you have figured out, if you just come to my office hours, we'll just do the homework together and it'll save you a lot of time. The rest of you, I assume, are just suffering alone, and that's on you. So that's basically it. Other than that, don't forget your weekly quizzes and that we do have a final exam whose date apparently has been posted by the university finally. So I don't know what it is, but you can find it in the materials. What was that? 18th. Cool. Any questions, comments, concerns? Fabulous. So today we will continue our discussion of algorithms for optimization, which is sort of the second or third or fourth, I don't know, I lost count, like big unit in this this course, essentially in our move from linear to nonlinear problems. And hopefully what you've noticed by now is basically algorithms aren't all that far off from what we did in the linear algebra part of this course. Essentially, we tried to take our optimization problems, map them onto some linear solve that system, and then basically the only new thing we're doing is wrapping an iteration around that because it was an approximation. So in some sense, these algorithms are very simple. But one thing that you've probably figured out by now is they also can be rather slow, right? So if we have an optimization problem in millions and millions of variables, then, for example, the sort of canonical technique that everybody would learn, other than gradient descent, is Newton's method, which is shown here on the screen. Here we have a gamma there for line search. And Newton's method is perfectly fine mathematically, but every one of the iterations of this technique is quite slow, right? And so this is a very typical trade-off that we encounter in the optimization world, where essentially we have to be very careful, right? That we have an outer loop in our optimization algorithm, right, which is probably the iteration of our method. And we have the objective function, which we're trying to minimize. And so far, we basically have 2 algorithms for optimization, right? Newton's method and gradient descent. And on this plot, probably Newton's method looks something like that if you have a nice convex bowl-shaped objective function at least. Whereas like gradient, so this is maybe Newton. And then like gradient descent, so remember that Newton, at least when you're close to a minimum, converges at a quadratic rate. Gradient descent converges at a linear rate, so probably it looks something closer to that. So here's maybe gradient descent. By the way, this picture makes it look linear. Eventually it flattens out. But hopefully by now we're beginning to understand that this kind of a picture is very misleading, right? Because from this kind of image, I think the obvious conclusion you should draw is like, oh, we should always use Newton's method. But why might that not be the case? Any ideas, just as a bit of a review? Yeah. Yeah, computing the Hessian is slow, and inverting it is even slower, right? So basically, the thing that's a little bit suspect about this plot is this object here, right? The thing that we're sort of equalizing between these 2 algorithms is the step that we're at in the algorithm. But here, in like Newton's method, for example, you've got this H inverse, which is extremely expensive to work with, relative to gradient descent, where you simply don't have that. In fact, notice that Newton's method and gradient descent are exactly the same formulation, just without the plus or minus that matrix. Yeah, and just in case that wasn't obvious. So essentially, what do we have? We have, like, from this perspective, optimization per iteration, objective function per iteration, rather. These two algorithms look vastly different because that's essentially what we proved theoretically. But the suspect part here is that iteration does not equal time. And it could be the case that we can do like thousands of gradient steps in the time it takes to do one linear solve in Newton's method, in which case it might not be so obvious that this plot is the right one to draw. Yeah? So in today's lecture, what we're going to try and do is make these two objects a little bit closer to each other. Namely, we're going to try and ask, like, can we get some advantages of Newton's method, like faster convergence, without having to compute and invert the Hessian matrix entirely? Remember, in root-finding lectures, we already had an example of an algorithm that did that, right? Like, for example, in one dimension, the secant method has this like weird golden ratio rate of convergence, which is somewhere between linear and quadratic. And we got it without actually needing to invert any matrices, right? And in fact, this Broyden algorithm kind of inherits a similar convergence rate. Now, we could apply Broyden's method directly to the problem here to approximate the matrix H, but as we've discussed actually a few times now, that kind of omits some of the structure that we see in optimization problems, right? In particular, I think the basic observation here is that the Hij can be obtained two ways, right? In Broyden's method, maybe you think of H as the derivative of the gradient vector, right? Because it's the second derivative of your function. But really, the definition of H is, whoa. I only had like 3 cups of coffee this morning. It's not enough. Is this quantity here, right? The second derivative of f in xi and xj. And one thing that we probably remember from calculus class is that partial derivatives commute, right? So in particular, this is the same as dxj dxi. By the way, this is a statement that requires proof, just FYI, which is hji. And so in particular, what you would expect is that the matrix that you're working with in Newton's method is always symmetric, right? And that is not the case in Broyden's method. Right? If you go back, you'll see there's no reason why just like a generic Jacobian matrix should be symmetric. And so essentially what we're going to do today is to see, like, can we derive algorithms that kind of look like Broyden's method a few lectures ago, but just introduce this additional structure, namely that your H is symmetric. And we're going to address a few other problems while we're at it. One is like kind of the units of the elements of the matrix, like making sure that essentially our matrix norm makes sense. And actually, Hamid, in our previous lecture, asked a good question, which is that one thing we aren't going to address is positive definiteness of the matrix H. We're still not going to address that in class today, but actually in the textbook, there's a condition on this algorithm we're going to cover today that shows when that H matrix is positive definite for free, which is kind of cool. I meant to mention that last time, but I was flipping through my notes this morning and realized. Okay, so these algorithms fall into a broad class of techniques. We're only going to cover 2 of them in this class. But essentially, there are 2 very exemplary techniques in a big class called Quasi-Newton algorithms, which is exactly what it sounds like. Like, you kind of want algorithms that look like Newton, but the quasi part means there's a fudge factor, right? And so the idea here is that we're going to try and approximate objects like the Hessian matrix, or its inverse, spoiler alert. But we're going to try and do so without calculating and inverting a giant matrix in each step of our technique. Cool? All right, and like really, Quasi-Newton is like a good vocabulary word. If you go on to fancy like higher order, more advanced courses in optimization or in numerical methods, like Quasi-Newton is one of the big things that comes up a lot in that universe. So here we're going to see 2 examples of that. You could easily teach an entire course that goes over different versions of these techniques, their convergence rates, their efficiency, what kind of objective functions they work well on, all that good stuff. I think in reality what happens, by the way, is that you'll take some piece of optimization software. So for example, in MATLAB, I think this is fmincon. In Python, it's probably something similar. I forget the name. And essentially, it takes a function pointer to your function and its gradient, and then just wraps around it in different ways, right? Like, they're just different formulas that kind of approximate the Hessian. So the good news is that it's often very easy to try many of these algorithms and see what works well in your setting. Also related to that, like, this is a dark art. Like, I think the dirty secret of the optimization world is that any of these algorithms kind of works equally well from perspective of theory. And so a lot of this ends up being engineering as to which of these algorithms works best for your particular case. But don't tell my colleagues I said that. Okay. So the typical assumption that we're going to make today, which I think is a very common one in the optimization world, is that you have a function whose gradient is known. For those of you in the machine learning world, you might ask, like, well, what if it's enough to know it up to just random noise? And for these algorithms, that turns out to be okay. But we either don't know the Hessian or we refuse to compute it, either because we are a lazy graduate student or because it's a big dense matrix or both. Yeah. One kind of middle ground that we're not going to talk about in this class, but you could also ask is like, what if we're willing to do Hessian vector products, which is a feature that is supported in some modern automatic differentiation tools. It turns out you can do a little bit better than these techniques. Not a lot, but a little. Okay, so this is our kind of common situation. You might ask whether this is natural or if it's just a byproduct of the kind of algorithms that we know how to write down. I would argue it's actually pretty natural. In particular, like let's say that I'm doing optimization on Rn, right? So I have an n-dimensional variable in my optimization problem. Notice that like it would be awfully ambitious of me to expect a step of my algorithm to take place in less than order n time, because at the very least, I probably want to like touch every element of my unknown variable. And so from that perspective, like requesting that you have access to the gradient is like sort of okay, because the gradient is sized the same as the unknown x that you're trying to compute, right? So like in other words, like from an asymptotic sort of like big O computer science perspective, computing gradient is probably kind of okay, at least from storage and oftentimes by efficiency as well. Whereas simply by asking for the Hessian, you have incurred a quadratic factor in your algorithm. Does that make sense? So this is, I think, like actually pretty reasonable set of assumptions. And then what the quasi-Newton algorithms all do is basically the following pattern where you define some matrix BK, and then in every step of your algorithm, you do maybe line search, maybe not, along BK inverse times grad f. So for example, if I wanted to implement Newton as a quasi-Newton method, what would BK be? Just the Hessian, right? And similarly, if I wanted to do gradient descent, what would BK be? Identity. Thank you. At least one person's awake. Okay. So those are two examples, and then what we're going to see is that there's a lot of things in between these that are kind of nice, like secant-style approximations of the Hessian. Cool. All right. So everybody on board with the high-level picture? We're about to dive into a big yucky calculation. You might notice this is a pattern in this segment of the course. We have a nice kind of elegant high-level story, and then we have like a nice high-level idea of an algorithm we want to implement, and then we spend the entire lecture doing yucky least squares calculations to actually fill in the formulas we need. But then the good news is once we've done that, we never have to look at them again, because the formulas themselves are not really so bad. Okay, so that's what we're going to do today too. Okay, so quick review here. Let's say that I wanted to do root finding on f just for a little digression. So remember how that works. So suppose that I wanted to solve f of x equals 0. This is not the problem that is on the screen right now. And I'm trying to find x. So in particular, remember that Newton's method in that case was something like this times f of x. I think that's right. And then we said, okay, we kind of had a similar set of motivations for why we might want quasi-Newton method in that case. In particular, this matrix is itself hard to compute. And so one thing that we did is we introduced an approximation that kind of looked like the secant method, right? In particular, let's say in this case that I have xk and xk plus 1. And now remember that kind of in the root finding world, we're all like one derivative lower. So we have like f and df as opposed to grad f and hf. Yeah? So in that case, we had maybe f of xk and f of xk plus 1. Then we said, okay, well, if we took df and we kind of like multiplied it by xk plus 1 minus xk, right? So if this is kind of like df dx, and this is kind of like dx, then what the approximation we introduce is that this is roughly equal to xk plus 1 minus f of xk. Right? And this is, for example, the motivation behind the secant method and Broyden's as well. Right? And as xk plus 1 approaches xk, notice this is just the definition of derivatives. So like this is actually a pretty reasonable thing. So what we're going to do now that we step up into a higher order derivative, now instead of df, we're going to have the Hessian, right? So we kind of have to like hop everything one derivative up, and what we're going to end up with is an approximation that looks like what's on the screen here. So this is like maybe a Broyden style update. Here maybe B stands for Broyden, which was, I can't say it was intentional, but whatever. Where you have your Hessian, and now if you look at the difference between the iterates x, right, the Hessian times the difference between iterates is going to give you the difference between gradients, right, because we're one derivative up. So we should take a second just to compare the formula that's on the screen with the formula that I wrote down on the board. Hopefully you guys are kind of tracking the difference. Here, what we've done is replace df by h. This is the second derivative on the left-hand side, so we need the first derivative on the right-hand side. Cool. So we could immediately plug this thing in, apply Broyden's algorithm as is from a couple lectures ago, and it's a reasonable optimization technique, but essentially we're going to do a little bit better today. Okay? And that's going to lead us to an entire class of algorithms. The kind of fun thing, which incidentally is new to the second edition of my book. So you guys should read these sections carefully because chances are there's lots of arithmetic mistakes. Sorry, in case you haven't figured it out by now, I'm not detail oriented. Essentially, we're going to introduce this style of approximation and show that like the details of where we arrange this approximation. For example, we put B on the opposite side with a B inverse. Each are going to lead us to a slightly different quasi-Newton algorithm. There's a whole class of things that does these sort of rank 1 style updates. And that, like, essentially what the book tries to do is prove one useful lemma that encapsulates a bunch of them and then plugs in different definitions for your vectors to derive each of the individual algorithms. This was my own little novelty, so hopefully it's correct. But we'll prove that lemma today, and then we'll show in particular we can derive two very famous algorithms in this domain. One of them is DFP, which is Davidon Fletcher Powell, and the other one is BFGS, and I forget the four guys' names who comprise BFGS. Okay, so right, so for some convenience here, okay, so now we have a slightly different, I'm going to erase this because I don't want you to get confused with root finding. I don't even want you to see it on the board. We have this new kind of Hessian style approximation times the difference in x's is equal to, or like roughly equal to grad f xk plus 1 minus grad f at xk. Now for convenience, because we're going to be working with these vectors quite a bit, we're going to give them names. So here we have sk, and here we have yk. I should give a note of caution. The most famous textbook in this particular domain, oh no, I'm forgetting the names of the authors. Oh, that's shameful. With the little butterfly on the cover. Nostal and Wright. So Nostal and Wright prove very similar set of lemmas. However, they and I disagree slightly on notation. In particular, they derive BFGS algorithm where like S is on the left, or on the left and Y is on the right, or something like that. And then they kind of just rederive the whole thing with the two things swapped. My dyslexia couldn't handle that, so I just kind of committed to one pair of letters for both algorithms. But this is all just to say that's a fantastic book. Just be a little bit careful reading it because their notation is different from my own. Okay. So this is our approximation. So far, we're in the land of Broyden's method, but we introduced two additional considerations. Now we are outside of Broyden world. In particular, we're going to add a constraint that B is symmetric. We also can actually check positive definiteness of B. This is something that we'll do a posteriori. So what we're going to do is to remove that constraint on B in our update formula, and then just check that for certain pairs of S and Y, for example, when F is a convex function, that turns out, I think, to be enough. Just kind of by accident, the formula that we'll derive makes B a positive definite matrix, which is kind of cool. Okay. So if we kind of go back to our previous lecture on Broyden's algorithm, this suggests the following approximation for our quasi-Newton method. So remember that B is going to be our Hessian approximation. And remember what we did in Broyden's algorithm is we said, okay, we've got this approximation, in that case of the Jacobian of our problem. And essentially what Broyden's method did was some kind of lazy approximation, right? It said, okay, we're just going to let our approximation of the derivative changed not very much, except we're going to add a constraint, which is that at the very least in this one-dimensional slice where we have learned a little bit of information by virtue of taking a step of our algorithm, we are going to update our matrix to satisfy this relationship as a constraint. Right? So actually the only thing we're going to add to that is one additional constraint, which is that B is a symmetric matrix, but sadly that makes our entire proof from that previous lecture fall apart. So now we have to go back and prove another lemma and do a lot of more ugly calculation than last time. Yes?
Is there intuition for keeping the matrix symmetric, like with the assumption that that's going to like help us in terms of like speed of convergence, or?
It's a good question. Yeah, like why bother, essentially. I think essentially the sort of intuition to have here is that B is supposed to approximate the Hessian. Any structure we can build into B that we know has to be there in the Hessian is likely to make that approximation more effective. And so this is a good case where if I remove that first constraint here, then the B that I get will not be symmetric. Like if you look back at the burden formula that you have, you can see that really easily. What we're going to see here is by adding this thing, what we're going to get is a rank 2 update of B. Spoiler alert. That actually tends to have a much higher approximation quality, which is kind of cool. Yep. Okay, so this is what we're after. But notice that I've done a thing that I think in this course is considered against the rules, which is in the objective function, I have not told you what norm. And of course, if we look back in our lecture on Broyden's method, the norm that we chose was just the L2, or actually the Frobenius norm. Sorry, I shouldn't mix those two up. Yeah? But even in Broyden's method, that choice turns out to be a little bit suspect. So as a review from last time, let's say that I'm optimizing. So let's say that my function here, f of x, y, is, I don't know, like the profit of my new company, right? And x is the investment, and y is the number of hours that I put into my work per day. This is obviously a totally made up problem, whatever. And because I'm a professor, I guess in my notation here, I'm minimizing profit, which is roughly accurate for my career. Okay, so if I'm trying to minimize my function f, so maybe I measure profit in dollars. I measure investment in, I could say also dollars, but just to be careful, maybe I'll make that euros. That's the euro sign, I think. I don't know. And then I have hours that I've worked, which I probably measure in hours. Okay, so here's the thing that I want to point out. And this is very typical in optimization, right? Like basically every input to f has a different scale, right? Like one of them here is in euros and one of them's in hours, right? And so essentially the thing that I want to be clear about is if I look at the Hessian, for example, d squared f dx squared, what units is this element of my Hessian? Like this is h11, right? I know you guys know the answer. Like just think like a physicist. Like if I differentiate a function, right? Like so if I you know I draw a path, so my units are in feet, then I differentiate, then I get like, you know, velocity, like feet per second. Here I'm differentiating twice, right? My numerator is in dollars, my denominator in this case is in euros 2 times. So what is my unit? Hamid, please help me out. I see you're dying to tell me. Yeah, it's in dollars per euro squared. This is a stupid unit, but whatever. Yeah. Now, if I look at another element of f, like dx, dy, like what unit is that object in? Yeah, dollars per euro hour. Which is like a good like disco band name. Okay, so what would happen if I took the Frobenius norm, like in my objective here? Is that like a particularly meaningful thing to do? Like it would take one number in this unit and square it, and take another number in that unit and square it, and add those two together, right? And so like from that perspective, I would argue that really putting the Frobenius norm in the objective of this problem is kind of weird. And in fact, this is not just like a weird, like a vibes are off situation. It's actually quite critical in the sense that like, let's say I define a new function like g of x, y, and I just make it f of 2x, y, like that. I mean, obviously these optimization problems should be basically the same, but if I put Frobenius norm in this approximation, it'll actually change because I've kind of rescaled the units of one of my elements. And so from that perspective, like, what would be a little bit nicer would be to choose a norm where the scaling of the individual elements of my vector, for example, doesn't have an effect on the approximation of the Hessian, because in some sense it should be a little more canonical than that. Does that make sense? Okay. So, right, so that's the basic issue here. So what happens in algorithms for quasi-Newton style problems is as follows. Essentially, we don't think that we don't think that the Frobenius norm makes any sense. So we define a slightly more generic object, sometimes like the weighted Frobenius norm or something like that, which we're going to write like this. And essentially, we're going to make it the A transpose W transpose A W, like that. And typically we'll choose W to be a positive symmetric matrix. So basically for every matrix W, there exists a norm through this definition. Of course, this definition feels super weird. Right? There's no reason why this should feel natural to you guys right now. But let's say, for example, that I chose W to be a positive symmetric positive definite matrix, which is usually a good choice in life. Then what is the one thing we know we can do to W? You're killing me. Cholesky, thank you so much. So I can write W equals L transpose, like that. And now we can write this norm in a slightly more familiar form. You might notice I'm doing a lot of this off the top of my head, which is dangerous, but also I didn't put it in my notes, so we're just doing it today. Okay, so in particular, this is A transpose, the transpose of this guy, which is L transpose, A, L transpose again, like that. And remember that trace has this nice property that trace of AB is trace of BA. Hopefully we're getting used. Do you guys see, by the way, this class has two tricks. We just apply them over and over again. So we're going to do that again. We're going to stick this guy over here. So this is, so notice you'd have L transpose, A transpose L, like that. Yeah, times L transpose AL, like that. Cool. So this is the same as L transpose AL transpose. I'll let you think through that real quick. Note I'm moving faster with these little identities because hopefully they're becoming a little familiar by now. So remember, so what is this? This is the trace of some matrix transpose times itself. Yeah. So in particular, this is the Frobenius norm of L transpose A L squared. Right? So from here, now it's obvious that this thing that I have defined is itself a norm for any positive definite W. And we can kind of see what's going on in this norm. Essentially, we're kind of using the Cholesky factors of W to rotate the rows and columns of A before computing the norm. We look confused. How can I help you out? What does this help the scaling issue? Fantastic question. Yeah. So there's two things. One is oh my God, you've added a Cholesky factorization. This is horrible. Now we have to do all this additional compute. And moreover, why does this solve any of my problems? These are both very good questions. So let's answer both of those. So for one, notice this proof is a theoretical proof. This is a way to justify that this formula is a squared norm, right? But that doesn't mean this is the formula we use in practice. Essentially, we're going to take all of our algorithms and write them in terms of W, meaning that we never actually need that Cholesky factor, which is nice. When we talk about preconditioned conjugate gradient algorithm, probably in 2 weeks because we're falling behind the course schedule, we'll see a very similar pattern. Now to your question, which is how does this fix any of our problems? Here's the kind of sneaky trick. We can choose the units of W to be something like 1 over the units of A. And as long as we do that, this product A times W we're going to find is unit free. And so it's basically, the trick is going to be to choose a W very strategically so that when we do that product, each of the elements that we get is going to have units that are actually comparable to one another. Now I haven't told you how to do that yet, but that's going to be the trick. Does that make sense? Yeah, that would be one reasonable thing to do. So like, for example, if like A were a covariance matrix, then, I mean, in an ideal universe, I would just put the inverse of the covariance matrix there, and then these two things obviously have an okay unit. Um, or I could normalize in some particular fashion, like, shift in scale. Now, these are not data matrices, they're Hessians, so it's not obvious that you can do that operation. But you have the right intuition, which is that like we want to find some efficient way to normalize so that these matrices are comparable to one another. That's absolutely right. But the basic high-level point that I want to give you for now is that we now have a degree of freedom. We have an engineering choice we can make, which is that W, and we can try and choose it strategically so that this norm makes sense. As an extreme case, for example, if W were A inverse, then very clearly this norm would make sense, but that's like a little too extreme. Yeah. Yes?
Is this definition for any vector yk and any vector sk, or is it like specifically in the universe of how you define yk?
That's a good question. So yeah, so essentially what we're going to do in our algorithm today is we're going to make a very particular choice of W, which is that we're going to say that W is any positive definite matrix with the property that when I multiply W by Y from the previous slide, in fact, it's on the top of the board here, that what I get is S. And what we're going to find is that actually the choice of W doesn't matter so long as it has that property. This is a little surprising. Yeah, and then what we're going to do, actually a little bit a posteriori, unfortunately this is like probably bad exposition, but it's the best I can do to fit into a lecture, is we're going to show that such a W exists and that it addresses our colleague's question about the units. Okay? Notice that already, like, it's sort of like doing what you would hope, like the same way that like B kind of takes things in S's units and maps them to things in Y's. Notice that W is kind of doing the opposite of that. It's like flipping them back in the same space. So it sort of feels like they're going to be comparable if we enforce that property. And I'll actually give you a formula for a W that has that property when we're done. Cool? All right, so now we're going to do a big ugly calculation. This is the pattern in this class. By the way, I'm taking my time with this lecture. I feel like at this point we might as well round to the nearest integer. This class is one lecture behind the written schedule, or like 2/3 of a lecture. So we'll just do that third and take our time with it. And then we'll catch up later. Or we won't. It's fine. It's my class. Okay, so in particular, we are going to prove the following lemma, which is beautiful if you want to appreciate it in its ugliness, which is to say the following. Notice that this is sort of an abstraction of that quasi-Newton step I wrote before, just to like eliminate some indices. So here I've got some matrix B naught, which you should think of as like the Hessian from the previous step of my algorithm. And I have a new matrix B that I'm trying to compute. And I'm going to try to optimize to find B that is the closest to B naught in this funny W norm, subject to two constraints. One is that B has to remain symmetric, and the other is that B times S is equal to Y. For now, S and Y are generic. And then what we're going to do is make special choices of S and Y and W for each of the algorithms that we'll derive in this class. Okay? So this is essentially like a convenience formula for a bunch of quasi-Newton things. But we are going to make one assumption, which is that W times Y is equal to S. And this is sort of our way of equalizing units, right? B goes from like S's units to Y's, right? That's what this constraint says. And W kind of takes them back. Yes?
Your justification there required W to be symmetric as well?
Yes, W should be symmetric and positive definite. Yeah, and we're going to show that that's an okay choice. Good question. Okay. So does everybody kind of understand our goal? Now notice, the formula that we're going to prove for B, it's like not very pretty. There's a lot of moving parts here. However, there is kind of a surprising thing about this formula in the lemma here, is that it has no W dependence. So do you guys see that this is the tiniest bit surprising? We don't know anything about W except its action in one slice, like this S comma Y space, and that's actually enough to determine B. So this is one of those cases where we didn't really need W at all for this algorithm. It's just like in any space where the units make sense, this approximation is going to work out. That's the way you should read this formula. The other thing to notice is that like, what is this update? Well, I minus rho ys is kind of like a projection matrix, right? In fact, it's exactly that. Like it kind of projects onto S and then moves things into Y space instead. So we're kind of adding a symmetric rank 1 thing to our matrix. That's the second term, and we're kind of projecting it out in the first one. Yeah, so that's the way to read this formula. The good news is that like when you're like a good little numerical coder, you don't think too hard. You derive this formula and then you carefully type it in. Or actually, spoiler alert: what's going to happen in our next slide is that we're actually going to be able to write the inverse of b, which is even better. Okay, so everybody on board? You ready to prove an ugly lemma? Cool. Notice, by the way, like the proofs in this class are ugly, but they're all the same. Like we have some least squares problem, we write its Lagrangian, we do some munching around, we cycle some traces, we make some friends along the way, and eventually we derive the formula we want. This is not a class where like the math proofs are like somehow very sneaky. Like they're kind of just following your nose and doing some very careful bookkeeping. Yeah. Okay, so let's do that. All right. Brace myself for lots of chalk dust. Incidentally, if you look in the first edition of the textbook, there is a proof of this lemma, and it's way worse than the one we'll do now. I'm sorry, that was a useful indiscretion when I was a graduate student, so I would strongly encourage you to look at the PDF that's in the Canvas page. Okay, so here's going to be our strategy, our sort of plan of attack here. We're going to try and do a change of coordinates that does two things at the same time. We're going to try to take the norm, and instead of making it the norm of a difference, just make it the norm of an unknown vector. So like kind of like db, something like that. And we're going to do a change of coordinates that turns W into the identity matrix. We're just going to do this all in one shot because we're all friends here. So in particular, because W is positive definite, just like we did on the board up there, you're going to factor W equals L transpose. And again, I want to emphasize that this is a theoretical proof. Like in the actual algorithm and the formula on the screen, we do not even need W at all. But we're going to use the Cholesky factorization just to make our proof easier. Yeah, this is actually kind of a nice example. Like Cholesky isn't just an algorithm; it's also a useful object for proving stuff. Okay, so we're going to define a matrix. We'll call it D, big D, which is going to be L transpose B minus B naught L. Notice this is going to kind of do two things at a time. Like for one thing, it's going to shift our problem to be, in the difference rather than in the new Hessian matrix. And we're going to change our coordinates to kind of incorporate the structure of W all in one shot. Okay? By the way, this proof looks a lot like the proof we're going to do in a couple of weeks of conjugate gradient algorithm, partially because they're similar algorithms and partially because I wrote the book, and so there's a particular kind of proof that I like to write. Okay. So if we reshuffle this expression, we can solve for B, which is just a question of rearranging these things. So in particular, we have the B is equal to B naught plus L inverse transpose times D L inverse. Does everybody agree with me so far? Cool. And notice, by the way, if I know D, I know B. If I know B, I know D. Right? Like there's everything else here is a constant. Okay. So in particular, one thing that we know from our constraint here is that B times S is equal to Y. And we can ask, like, what does that imply about our matrix D? Yeah. So in particular, what do we have? We have B times S equals Y. We have a formula for B. B naught plus L inverse transpose D L inverse times S is equal to Y. Like that. Cool. So if we reshuffle this expression a little bit, notice like this guy is a constant, so we can kind of just move B naught times S to the right-hand side, right? Because the thing that we don't know in this expression is D. And we can pre-multiply by L transpose. What we're going to get is D L inverse S is equal to L transpose Y minus B naught S. Does everybody agree with me so far? Cool. So remember, the only unknown in this entire expression, like it looks ugly, but that's in the eye of the beholder here. These are all constants. The only thing that is not a constant is D. That's the thing we're trying to solve for. So a useful thing to do in this proof, out of mathematical laziness, is to say, okay, well great, let's just give this object a name. Let's call it little w. And let's call this thing little z. So in other words, I have D times little w equals little z, and hopefully you agree with me that like if I can find d, I can kind of reverse engineer and go all the way back to the solution of my original problem. Cool? All right. So here's the good news. We had a constraint on b, bs equals y, and basically what we've shown is that like an identical looking constraint now applies to our new unknown matrix D. So nothing surprising has happened in the constraints, but if we're going to do this change of variables, we also have to check the objective, right? So we have this constraint. I mean, if you're wondering, like, how did I make that, guess that substitution? I reverse engineer it so that this happens, right? Like, there's nothing smart here. Like, essentially, we're just going to do our math in this, like, alternative upside-down universe where all our coordinates are rotated by L. That's essentially all we're doing here. Okay, so moreover, remember that our objective is B minus B naught in the W norm squared, which, as we showed before, is L inverse transpose D L inverse W squared, like that. Okay, that's what we showed before. Or sorry, when I say showed before, I mean B minus B naught is L inverse transpose D L inverse. Sorry. Okay. So now let's take this expression and write out a big ugly formula and show that a nice thing is about to happen. So in particular, what is the definition of the W norm? Well, unfortunately for us, it's like not super fun, but we've got, remember that it's kind of like this guy transpose times W times that guy times W again. I see two hands, so I must have made a mistake. Where is it? Yes. Uh-huh. Yeah, that's right. Yeah, that's another way to write it. Yep. Hamid. Oh, that's true, actually, which I didn't bother to do in my notes. Oh, we can do it again. That's okay. We'll just go back to the definition. Yes. Is this a niche or a question? Yeah.
Just a quick thing.
Uh-huh.
So I think you have like WS equals Y, and then
Yeah.
substituted in B naught plus L inverse transpose D L inverse for W.
Mm-hmm.
I'm just, why does that equal W then?
Oh, sorry. Sorry, I was being agreeable, but I actually don't agree with you. So on the third line.
Yeah, that one.
Yeah.
Is that from like the assumption WY equals S?
Yes. No, it's from the assumption BS equals Y. Yeah. Okay. In fact, it is exactly the BS equals Y. Yeah. Okay. Right. So if I write my formula for the W norm, as Hamid has pointed out, we actually kind of already did this, but that's okay. So we have the transpose of this matrix, and then we have W transpose, if we're going to be careful, times this matrix again. Times another W. And notice what's going to happen. Like essentially, we already know that W is LL transpose, right? So this whole product, you know, if I put in an LL transpose like that, right, is actually just the identity. And similarly, if I cycle this piece to the left-hand side, you'll get another identity matrix. So really, this whole expression is just the Frobenius norm of D squared. Cool. So basically all we did was a change of coordinates to get rid of W. And in the process showed that basically an identical looking constraint still holds. The details of the constraint are different, right? Like now W and Z instead of Y and S, but the sort of form is the same. Okay. Have I managed to miss you guys yet? I can try harder. Okay. So in particular, what we've shown is that our optimization problem is kind of equivalent in our rotated coordinate system to the following, which is, I'm going to stick a 1/2 just for convenience, the norm of D Frobenius subject to the constraint that D is D transpose. Notice that like this change of variables didn't really affect the symmetry of D. And dW is equal to Z. Okay? So in some sense, like all we've shown so far is that like the introduction of the W norm didn't really change our problem. Like if we'd just done Frobenius to begin with, we would have ended up, like this is just a slight generalization of the original problem. Okay, any questions so far? So here's gonna be our strategy. We've done this change of variables. We're going to derive a formula for the minimizer of this problem, which is a special case of the one on the board where W is the identity, basically. And then, well, in principle, what we'll do is substitute back in our formula for B in terms of D and get a solution to the original problem. Or probably what I'll do, because I'm lazy, is say, one could substitute our formula in and get the thing on the board, because it'll get a little ugly. Okay? Yes, Alice. Mm-hmm. You got it. Yeah. Like essentially, this is a slightly more generalized version of the problem than the one that I've written here. The only difference is the Frobenius norm versus the W norm. But doing that, we could have just written the KKT conditions, or sorry, the Lagrangian of this thing directly. It just would have been uglier. So this is basically a convenience to eliminate a little bit of our headache. Yeah. Any other questions? These are great questions. I'm glad you guys are paying attention. This is great. Yes. No, and I'm realizing now that the choice of little w as notation here was perhaps not the best. But we're committed now. Or there probably is a relationship, just to make things a little worse. They are related because there's an L in there, but no, not in any intentional way. I was just stupid. Okay. Great. So now all we have to do is solve this thing really quick, and then we're done with our proof. Cool. All right. How do you think we're going to do that? Well, we're going to write the Lagrangian, take the derivative, like turn around 3 times, clap our hands, and then a formula is going to come out. Okay. So let's do that. If I were a better instructor, I would just call on one of you guys to do this on the board at this point. Strike fear in the hearts of our graduate students. Okay, so I'm doing this partially because notice that our calculations in each of these lectures are sort of it's sort of like we keep circling on the same thing. These are least squares is basically the only topic of this course, but each time we do it, we make it a little more complicated. So now we have least squares. We have a matrix unknown. We kind of introduced that in our Broyden method. And moreover, we now have sort of a matrix structural constraint, like it's equal to its transpose. Yeah? Okay, so what's going to be our Lagrangian? So, right, so now we have our unknown is a matrix B, like that. And maybe we have 2 Lagrange multipliers. Let's see, we haven't used the letter A yet, so maybe the letter A we'll use for the first constraint. Notice our Lagrange multiplier needs to be a matrix for the symmetry constraint, right? Because there's actually n squared constraints. Or really n times n minus 1 over 2, but that's a detail. We're going to get rid of that. And we need a vector worth of constraints to satisfy the second guy. So it's mildly ugly, but not too bad. Okay, so what's going to be our Lagrangian? Well, we have our objective, which maybe we write like this. And now we need the dot product between our Lagrange multipliers in each of the constraints, right? So the dot product, we have A transpose times maybe D minus D transpose. I actually don't remember in the textbook which sign I gave this thing, so we'll just do it live and get confused later. And then the dot product between our vector and dw minus z. Hopefully we all agree this is Lagrangian in this problem. Hopefully by now this calculation is starting to feel natural. Basically you take your objective function, you introduce a Lagrange multiplier for every single constraint, which means that if your constraint expression is a matrix, you have to have a matrix valued Lagrange multiplier. And if your constraint is a vector, like the second guy has to be a vector valued one. And remember that transpose, the trace of a matrix transpose times another matrix. This is the dot product. It's the sum of Aij times Bij. Yeah. Oh, good. I anticipated it this time. Excellent. All right. What are we to do? It's important not to think too hard. We're going to just take the gradient of this thing and see what happens. Yeah? So in particular, we have that 0 is equal to the gradient with respect to our unknown D of the Lagrangian. Get excited. So What is the gradient of the trace of D transpose D divided by 2 with respect to D? I know you guys know the answer. This is just the norm of D squared. So what's its gradient? One more time. Well, there's 1/2 in front of it. All right, on 3. 1, 2, 3. A little louder this time. Ah, God. All right, yeah. So the gradient of that first term is D. Okay. Now here's kind of a fun thing. Notice that this is the dot product between A and D, right? A trace of A transpose D. So if I differentiate that with respect to D, I'm going to get A. And this is kind of like the transpose of that. So it's A minus A transpose. Does that make sense? Okay, and now, oh good, this is matching my notes for once. We actually derived when we did the Broyden lecture, the derivative of this last guy, which is lambda W transpose, like that. This isn't too bad. Okay, now this is kind of an interesting object. It's a matrix minus its transpose. Does anybody know what this like what a property that this thing has? Let's call it Q maybe. It is anti-symmetric. If I take the transpose of Q, I get minus Q. Yeah? Okay. So in particular, this thing is D plus Q minus lambda W transpose, where I know that Q transpose is equal to minus Q. I might know some other stuff about Q, but that turns out not to matter. Okay? Everybody with me so far? Okay. So, oops, wait, I have D. Oh, you guys didn't, oh, no, yeah, this is right. So in particular, oh, I'm going to do an annoying thing that students hate. I'm going to call this minus Q and put a minus there, just for, because of laziness, and if this doesn't match my notes, I'm going to start making a lot of mistakes. Okay? Yes? No, I mean, I just defined Q right here. I'm just going to flip the definition of Q to be A transpose minus A. What was that? This guy? No, actually, yeah. The derivative of A transpose D with respect to D is just A. Yeah, so this is correct. I'm just going to define Q to be A transpose minus A. That's all. I'm just changing my definition slightly. Oh, no. Oh, it kind of doesn't matter. Notice that if D is equal to D transpose, then minus D is equal to minus D transpose, so you can kind of put whatever sign you want there. Yeah. Okay. By the way, when we do KKT conditions, probably in our next lecture, because I'm talking slowly, then we will have to be careful about that sign. Yeah. Okay. Good. So I've only mildly confused you guys. So in particular, we have D is equal to Q plus lambda W transpose. I just want to do it because I think this formula is a little nicer than minus Q. That's all. Okay. So here's going to be kind of a fun, here's a fun thing. So remember, D is a symmetric matrix, right? That's sort of our whole point of this problem. So one thing we know about symmetric matrix is if I take a symmetric matrix and I average it with its transpose, what happens? Nothing, because it's equal to its transpose, right? So it's like averaging a matrix with itself. So in particular, we have D is equal to 1/2 D plus D transpose, just for fun. Now, why would I do that? Well, okay, so I have 1/2 Q plus lambda, lambda W transpose, like that. And now I have D transpose, so plus Q transpose plus W lambda transpose, like that. Cool. Now, remember, Q transpose is minus Q. We've got a Q and a Q transpose, so those two terms actually cancel, right? So this is just a sneaky way of killing a term, yeah? So in particular, I have this is equal to 1/2 lambda W transpose plus W lambda transpose. And this is a really nice formula. Do you see that? In particular, we've shown that D is rank 2 at most, yeah? And moreover, we've basically exposed D in terms of like relatively few unknowns here. Any questions so far? Okay. So now we're still not done. Like we need to solve for lambda at the very least. So we need to simplify expression a little more. Okay. Here's where things get ugly and a little bit delicate. So we're gonna do this together and go on this emotional journey. So what have we done and what have we not done? I mean, so we've taken optimality with respect to D, but remember Lagrange multipliers, we also have to make sure that we're optimal with respect to all the other Lagrange multipliers, like A and lambda here. So, and which is basically the same as saying we need to enforce our constraint, right? So far, we actually have enforced the symmetry constraint. We kind of did that sneakily. So the one that's left is the one that says that, oh no, I erased it. That remember that we have dw is equal to z. Right, that was in our original formulation. And that's the thing that's missing, and that's what's going to help us determine lambda. Does that make sense? Okay. So, out of laziness, I'm going to do something kind of weird, which is, what is 2 times z equal to? Trick question. Well, it's equal to 2 times dw. Okay. And in particular now, we have an expression for d with a 1/2. This is just out of laziness. Yeah. So in particular, this is lambda w transpose plus w lambda transpose, like that, times w. Yeah. So here I just substituted in that expression here. Okay. Now here's kind of nice thing. If we reparenthesize this expression, notice that like a kind of cool thing happens. It's like kind of like coordinates. So we have a dot product between w and w here. We have a dot product between lambda and w there. So in particular, we can write this in a very different fashion. So we have a lambda w transpose w. So we can say that's the norm of w squared times lambda plus we have a lambda dot w there times w. Isn't that cool? That's like a kind of a fun, like a little sneaky trick. Okay. So yeah, so in particular, what do we know? We like kind of have coordinates, which are determining z from lambda and w. Moreover, remember that w is a constant. The thing we don't know is lambda. Okay. So one thing that we can do is take the dot product of both sides with w. So basically, we're going to like solve a 2x2 linear system. We're going to take the dot product of both sides of this expression with w and with lambda. And then that's going to give us literally a 2x2 linear system. We can solve it and then recover our coefficients here. Okay, that's our strategy. So in particular, if I take the dot product of the left-hand side with w, I get 2z dot w. So surprising, I know. If I take the dot product of the right-hand side with w, let's think for a second what's going to happen. We'll get norm of w squared, lambda dot w, yeah? Lambda dot w, w dot w, which is norm w squared. So actually, a kind of tidy thing happens, which is this is just 2 norm of w squared, lambda. Everybody agree with me? Okay. So in particular now, why bother doing that? Well, notice we can kind of, by the way, we're going to assume that w is not equal to 0 or else our original optimization problem is kind of goofy. So in particular, we now have an expression for this lambda dot w term here, right? So we can write, just by plugging in this expression here, that 2z is equal to the norm of w squared times lambda plus lambda dot w, which is basically z dot w divided by the norm of w squared times w, like that. Everybody agree with me? It's getting silent. It's getting quiet in here because the calculations are getting ugly. I know. But I think so far we haven't made a mistake, which is good. But here's the thing. What is the unknown in our problem? It's lambda, right? Everything else in this big ugly expression is a constant. Yeah? So in particular, notice I have lambda times some coefficient plus a bunch of other stuff, you know, in my equality. So I can actually solve this thing for lambda just by dividing by the norm of w squared. Yeah? So what I get is the following, which is ugly, but it counts as an expression. I get lambda is equal to 1 over mod W squared. I'm so sorry that I'm left-handed, so I keep getting in front of the math here. But like the good news is you're all taking notes and doing all this math in your head anyway. Times we've got 2z minus z dot W over the norm W squared times W, right? That's this expression here. Like that. Right? So basically all I did was just rearrange this expression. I promise our ugly arithmetic is almost over. We're so close. We can taste it. Also, I taste plastic. Something is burning in the front of the room, but I might be having a stroke. Okay. So if we expand this, this product out, what are we going to get? Well, we have 2z over the norm of W squared. Like that. And then the second one, we've got kind of an interesting expression. It's z dot W. We've got a W squared and a W squared. So this is the norm of W to the 4th times W. Cool? Now here's the thing. We're actually done. Do you see that? This is an expression for lambda in terms of stuff that we know. Yeah? So now it's just a question of unraveling everything. You're plugging this guy into this guy, expanding it, simplifying, plugging that guy back into our original substitution, and then we'll be done with our problem. No biggie. Mihir, what can I do to help you out? Yeah. They're very nice. Yeah, which if you look at this expression, notice that you see a bunch of projection matrices. So like it's like totally unsurprising that that happens. Yeah, good observation. Really, it smells like plastic right there. Okay. So let's unravel all the stuff that we've done, pay for the sins of our substitution here, and then derive our final expression. So remember that D is the average between lambda W transpose and W lambda transpose. We now have a lambda, so we got to plug that here and see what happens. Okay. I'm going to erase this board. Everybody cool with that? Good. Got to remove the evidence, you know? Okay, so we have, from before, we've got D is equal to 1/2 lambda W transpose plus W lambda transpose, like that. Now we are going to substitute in lambda. Everybody get excited. This is going to be 1/2. Now we've got lambda here, right? So this is going to be 2z over the norm of W squared minus z dot W over the norm of W to the 4th times W transpose, halfway there, plus W times this darn thing transpose. So we got 2z over the norm of W squared. Somebody put me out of my misery. Z to W. I've got like, let's try that again. Z W the 4th W transpose. Ta-da. Beautiful. Okay, but now we're going to simplify our expression a little bit. So here's one thing to notice. Notice that we've got like a W transpose here, and a W transpose there. That's kind of nice. So we have two terms that are going to group together. And then notice we've got like a Z W transpose times 2 over the norm. Yeah. And we've got a W Z transpose times 2 over the norm in the second term. So everything is kind of feeling symmetric, which is good because the whole point of this problem was to get a symmetric matrix. Yeah. So if we couple together all those terms I just pointed at and confused you with, then what are we going to get? We will get like a 1 over the norm of W squared like that times Z. Notice there's a 1/2 and a 2 that cancel, and a Z W transpose like that, and a W Z transpose. Oops, I don't know why I wrote the 4th. transpose, right? So that takes care of two of our terms. But the other two terms are actually the same. Do you see that? Because you have W transpose with a minus Z dot W over W to the fourth. And similarly, you have W transpose times minus Z dot W over W to the fourth. A lot of words. So minus Z dot W over W to the fourth, like that. W transpose. Ta-da! Schwitzing. Okay. So here's our formula for D. And notice it's actually not so bad. I mean, like, essentially, what did we get? We got, this is sort of like rank 2 or 3 looking. You have this guy, which is kind of accounting for the fact that you need to take W to Z or vice versa. And then this diagonal update here. And that's basically it. It's like not such a bad formula. And the very good news is even if the proof here was a little bit algebra-y and gross, you could very easily type this thing into your computer. Like that's not a big deal, right? And moreover, essentially we still have one thing to do, which is so now we have solved our simplified problem. What we really want is B, right? And remember that the whole point of this was that B is equal to B naught plus L inverse transpose times D times L, like that. Inverse. So what are we going to do next? Well, we can substitute this thing in here. And I'm not going to do this because, like, for God's sake, like, enough already. You people, like, you get what this calculation is going to look like, right? But essentially, once the smoke clears, it'll be exactly the formula on the bottom of the slide. And really, there's nothing exciting here. It's just a question of unraveling a bunch of definitions that we did. Is everybody comfortable with that? You can make my carpal tunnel worse and bring me great sadness for your understanding, if that's what you want from your instructor. Just raise your hand, it's fine. I won't judge. Okay, good. Right, so basically that concludes the proof of our proposition here. Stepping back, because I know that was ugly and there was a lot of steps involved. Notice, by the way, the steps really were pretty straightforward. I want to be clear about that because I think it's easy to look at these proofs and be like, oh my God, what the heck is this guy doing? He's like making substitutions, he's moving things around. But really, there's just two key things that happen here, right? One was a clever change of variables to get rid of the W matrix. And when I say clever, I kind of mean just like plugging in all the stuff that you hope is true. And then the other one was just computing the KKT conditions and grinding through it quite a bit. Like, oh, sorry, when I say KKT conditions, this is anticipating our next lecture. I really mean the Lagrangian condition, like setting the derivative to 0. Yeah? And so that's my basic point, is that's all that happened in the proof. The rest was just algebra. It's ugly algebra, which is why we're doing it on the board and not on your homework, but really, like, this isn't a proof that like required really clever argumentation about some weird variety or anything like that. This is all just very straightforward least square stuff. Yeah, Hamid.
I still don't understand where the L just goes away with the
We don't understand where the L goes. Okay, let's see how far we can get. You know, okay, so if we go back, we were going to substitute this thing in here. What's going to end up happening if we go, remember that way back we made a substitution like 3 days ago. Remember that we have W is equal to L in, Alice, don't you tell him it's okay. Okay, W is equal to L inverse S. And moreover, yeah, I heard that. We had that Z was equal to L transpose Y minus B naught S. Remember, this was the substitution that we made to derive that simplified problem. So here's what we're going to do. Oh my God, I'm not going to do this. I'm sorry, Hamid. But what you can do is take these two expressions here and plug them in every time you see a W and a Z. And notice now you have inserted L's into this expression, right? And now those L's are going to cancel with those L's. Is that enough? Is that enough for you? What was that? Well, that's right, but that's going to end up being okay. They'll group together and you'll get W's, and those are going to cancel W's in other places. Yeah. So fine, I'll put it on your homework. Great. It's also in the textbook. The textbook goes through this calculation carefully, but just out of no, I'm not doing that. It's too much. Like it really, there's nothing exciting. It's just a bunch of algebra, but I promise you it works out. Yes.
I guess this is already erased on the board.
Excellent.
In general, when we have this like symmetric constraint,
Mm-hmm.
can we effectively ignore it into Lagrangian? Because when the way that we got rid of like
Oh, no. Yeah, that's a good question. So like I kind of did a weird thing, which is I introduced the Lagrange multiplier and then like 2 seconds later it went away. Yeah. No, but notice I used anti-symmetry of the Lagrange multiplier to make that argument. And that was absolutely critical. So if you wanted to, there's a slightly different version of this thing where you only enforce the constraints on the upper half of B, because if you think about it, that's kind of enough. And then that doesn't go away and you have to solve for that Lagrange multiplier. But one way or the other, yeah, you absolutely need that constraint. Yeah. And by the way, like where did the symmetry of this expression came from? It came from averaging D with its transpose, which you could only do by virtue of that anti-symmetry. Yeah, so it's critical. I just used kind of a mathematical lazy sleight of hand to get rid of it quickly. Yeah. Incidentally, you didn't have to do that. Like if you didn't see that trick, you could have absolutely solved for the Lagrange multiplier, plugged it in, and you get the same thing. Yeah. All right, I'm gonna move quickly before Hamid asks another hard question. Okay. So in any event, the good news is that we still have some just very simple update for our matrix B. And this directly leads us to an algorithm called Davidon-Fletcher-Powell, which is exactly this. So what we do, if you recall, before we wrote all that horrible math, is we wrote this particular optimization problem down where like we're thinking of B as our replacement for the Hessian, S as being the difference between successive iterates, and delta F being the difference between successive gradients. Now we just have a formula for the optimal B, right? So long as we choose a W in this weird way. We're going to put a pin in the choice of W. We'll come back to that momentarily. And now, if we just plug in this formula here, this is called the Davidon-Fletcher-Powell update, and this is basically directly gives us a new algorithm for optimization, right? So what are we going to do? In each step of our algorithm, we have Y and S in terms of our last two iterates and the gradients of those 2 points. We plug in this formula here to update B, and then we can take another Newton step. Does that make sense? Now, what is the expense of this algorithm? Well, there's kind of 2 pieces. One is we got to update B, and then the other is we actually didn't want B, we wanted B inverse, right? So in order to take a single step of this, it's actually very similar to Newton method. We have to invert this matrix, and that's not so great, right? So kind of unsurprisingly, given our discussion of Braden's method, what we find is that, and no, I mean, I'm not proving this lemma. Now I'm picking on my student. That if B takes the form that we've written on the slide here, then B inverse takes the form at the bottom of this proposition. The proof of this lemma is wildly uninteresting. You just take these 2 matrices, multiply them together, and do a bunch of simplification, and eventually the identity falls out. But essentially, what does this mean? Well, remember what we did when we talked about Braden's method. Rather than updating our approximation of the Jacobian in that case, we just directly updated the approximation of the Jacobian inverse, right? Because now, when we take a step of Newton, right, what we're really multiplying by is B inverse. So here we just keep that guy around as a matrix rather than B. Does that make sense? And so that's the DFP algorithm in reality, is that you can call this matrix some other thing like M, right? And so in every step of this algorithm, you apply this update here, and then you take M and you multiply it by the gradient of F, not M inverse. And that is the step that you take in optimization. Does that make sense? Yeah, so this is DFP. I think historically, this is one of the very first Quasi-Newton algorithms that was derived, and indeed it's in all the standard software packages, like it's easy enough to play with. As we discussed a couple lectures ago, just like in Braden's method, there's a variation of DFP where you just keep track of the last few iterates and you kind of build up B or B inverse just from the last like 10, say. This is called limited memory DFP, where you kind of have a sliding window that happens. Either one of these is totally reasonable. However, in our last, 5 minutes, we're going to derive one more algorithm, which I think is actually the one that most people use in practice. This appears all over the literature. This is the default choice in most optimization software outside of machine learning, which has a bunch of other considerations because of the stochasticity. Which is the kind of interesting observation, and this is really clever back in the day. And it's kind of cool because this is one of these algorithms that like everybody made the same observation at the same time. So it like appears in like a bunch of different research papers back in like I think the 1970s or so. And the idea was as follows. Remember that like the whole point of these updates in Broyden's method and then now in DFP is that we're just being lazy with our Hessian approximation. We're saying like, we only get one new piece of information, so like the Hessian really shouldn't change that much, you know, from step to step. So we just optimize this thing on the left-hand side as our objective function with two new constraints, right? Symmetry and that b times whatever equals whatever else. I forgot. Yeah. Now, in the previous slide, in DFP algorithm, the thing that we actually update is this matrix B inverse. Notice this thing can actually change a lot from step to step. Right? That's not our optimization objective. Right? Our optimization objective is that the inverse of this thing, like if you invert twice, that's the thing that doesn't change very much. And in fact, notice, for example, here, there's a 1 over dot product kind of hiding in this formula here. So like numerically, like this is a good source of like things blowing up. I'll let you kind of go back and think about where this happens. It's kind of like when the search direction and the gradients are orthogonal to one another. So the DFP algorithm has a drawback, which is the Hessian approximation's inverse actually can change really quickly, yeah, which is a little subtle. I mean, think about the difference between 0.01 and 0.0001. Those numbers are like close together, but 1 over those things are very far apart, right? And that's essentially what's going on. And so the standard algorithm that everybody uses does a sneaky thing. It says, okay, we're gonna not only approximate BK inverse, that is the thing that we're gonna say should change very slowly. This is kind of cool, right? So essentially in this Quasi-Newton method, what we're gonna do is say, okay, we're gonna do a new matrix C, which is gonna be our approximation of the inverse of the Hessian, yeah? And now we're going to write a very similar optimization algorithm to the one that was in DFP. Notice it's actually kind of identical in form, but I did one sneaky change, which is I swapped y and s, right? Because the inverse Hessian times the difference in gradients should be the difference in points. Yeah? The optimum of this is not the optimum of the previous problem we wrote down. They're completely different, but you can apply the lemma that we derived all the same, right? It's just you have to relabel all your variables. So this algorithm is called BFGS. It stands for 4 guys whose names I have forgotten. This is the update. Notice it basically looks the same as before. Notice also you don't need to invert this matrix because it already is an approximation of the inverse. So this is directly the formula that you would use in BFGS. Now, one final thing in our last 2 minutes of class to go back to a question we had all the way at the beginning. All of this was contingent on finding a W with a particular property. Right, so essentially one thing that is actually mentioned in the textbook is the following. Essentially, one thing you might notice is like none of these formulas actually have W in them. So really all we need to do is convince ourselves that a W exists, and that's enough for these algorithms because we never actually use it. It's really just a way to derive these techniques. And so in particular, here's a choice of W that justifies BFGS algorithm, which is kind of cool. So if I take W, to be the following, the integral from 0, 1 of the Hessian of my function evaluated at x plus tau s ds. So what is this thing? This is super cool. So essentially, remember that what we really wanted was ws equals y, right? Essentially what's happening here is if I draw a line from x along the search direction, kinda, and I average the Hessian along that line, one thing that you can check, we're out of time, so I'll let you do that at home, is that this thing actually satisfies this property here, meaning that like it's totally fine for us to use that as a sort of motivator behind the algorithm we've written down. Now, I want to spend just a second giving some intuition why this is such an exciting and really cool idea. Oops, sorry, I bumped into my keyboard. Now, what is this thing? This is the average Hessian kind of between the previous iterate and the next one, something like that, like just drawing a straight line. Now remember, our whole point was to choose a W that cancels out the units, right? That's the thing that we wanted. What are the units of C in BFGS? Well, they kind of look like Hessian inverse, right? What are the units of this thing? Well, they look like Hessian, right? There's just a bunch of average of Hessian. So you multiply these two things together, this quantity becomes unitless. And that's sort of what's justifying why the BFGS algorithm is independent of scale. Really sneaky, yeah? Now, to be absolutely clear, this is like essentially what you should do at home is check that this definition satisfies two things, WS equals Y and W being positive definite. Notice if F is a convex function, then this is positive definite for free. And moreover, WS equals Y is basically just a consequence of the fundamental theorem of calculus. And so when we put all those things together, essentially we have some matrix that cancels our units, and now all of the algorithms we had in the last couple of slides fall together. And the kind of cool thing and surprising thing really is that the choice of W is irrelevant. Any W that satisfies this one property will give us the same optimum, which is surprising and weird. I mean, you'll have to look back at the proof to convince yourself that's the case. Okay, I see your hand. One more second. Right, so then what I should note finally is that the standard algorithm and the one that really everybody uses in practice, you've probably seen this if you've ever played with optimization software, is called LBFGS, and now you guys have all the pieces to put this algorithm together. So in LBFGS, you keep track of the last like L iterates of your algorithm and the last L gradients. You build up your Hessian approximation by recursively applying this formula a bunch of times, starting usually from the identity matrix for like some fixed number of steps. And that is the Hessian you use to get to the next step. And the kind of cool thing about LBFGS is you don't have to invert a matrix, right? C is already the inverse Hessian. So implementing this is just a question of writing kind of a nice recursive piece of code. There's a question here and a question here. Oh, is it d tau? Oh, you're right. I'm sorry. Thank you. Yeah, sorry. S is the vector. Tau is a scale. My apologies. All right, folks. So with that, maybe we'll stop today. We're officially exactly one lecture behind our old course, but that's good because at least it's quantized the same as before. In our next lecture, we will talk about optimization with constraints. In particular, we are going to derive a thing that many of you have probably seen before called the KKT conditions, which is kind of like set the Lagrangian of your problem equal to 0, but now we're going to have inequality constraints in our problem. And then we'll talk about methods like barrier method and active set method, which is how to take what we just covered the last couple lectures and lift it to that case. So with that, don't forget your homework. Don't forget to open the next homework. Have a delightful weekend, and I will see you all later.